So we're looking at obtaining the minimum diameters along the length of the shaft. Right, so we'll be using these equations for that. Right, so this is for if you have a shear force alone, and then this equation here is for if we have a bending moment or a torque or both. Right, so we calculated these bending moments. We have calculated this torque. We have sigma yield, we have Sn, energy factor, safety. So what we're missing right now is Kt. So that's our stress concentrated values. Right, so again, stress concentration, Kt. And we could recall stress concentration, these preliminary values was obtained for initially, just for example, where the bearings have to sit and where components have to sit. So where the bearing has to sit, we would say there's a Kt of 2.5 because there's a sharp fillet where the bearing has to sit. If we have a component, an element, we could say here it's a well-rounded fillet, which is 1.5. Right, so we'll be good applying this to different regions along the length of the shaft. You could see here for if we have a retaining ring, which we will need this to hold the gears, Kt will be 3. And for key seats, the profile key seat is 2, which is what we had specified in the question. So we'll be using these Kt values in those equations to calculate the minimum diameters. Now, going back to this here, we need to arrange the shaft, right? And the question gave the layout of the shaft. For example, we have the gear, we have the bearings, and then we have the output gear. Right, so in order for the gear to drive, there's a key. And in order to keep the gear in place, there's a retaining ring or a circlip groove. And the gear is pushed against the shaft here. So this is our shoulder. So immediately one time we could see here at point A. Right, so at point A there is already 3 diameters we could consider. We could consider this region here where Kt is equal to 3 for a circlip. Right, but at this point also the torque is equal to 0, because if you could recall, we said that the torque comes in here, goes through the shaft and flows out here. So that's how the torque goes through the shaft. So at this end here, at the end of the shaft, there's no torque. The torque is only from inside here goes out. So the torque would be 0 at this point. And of course the bending moment would be the bending moment MA at this point, whatever it was calculated to be. Right, now next step is to look at the key. So we have the kiwi here. So in this case, we need to get Kt. So that will be from the previous note, right? And that Kt value was actually 2. So that Kt value for the key was 2. Right? And we said that it has a torque, because the torque is flowing through, and then there's the bending moment. Right, so the torque is what was calculated before. So at this point now, we move on to the shoulder. And we say that for a mating surface, we have a well-rounded fillet. And that well-rounded fillet has a Kt value of 1.5. Right, so that's highlighted there, 1.5. So that Kt value here is 1.5. Again, there's a torque, and then there's the bending moment at that point. So we could see at A there will be 3 diameters, D1, D2, and D3. So there will be 3 minimum diameters. And what we will do, we will choose, of course, the larger of when we calculate those 3 minimum diameters. Now, this is being done in Excel, so it's a matter of dragging equations. So we enter the equations once and we drag it down, and we will see D1, D2, D3, we take the larger one. The next step we come across here now would be point B, or region B. So again, we have a step up in the shaft. So this step up here will be a well-rounded fillet. So the KT will be 1.5. Again, there's the torque, and then there's the bending moment at B. Next, there would be the keyway. Right, so the keyway, the KT for this was 2. Again, torque and bending moment at B. So you substitute those things in the equation. That's why I'm writing it here. And then the last here now, this actual fillet, this would be a sharp fillet because it's for a bearing. So KT in this case would be, and it's given here, for a sharp fillet is 2.5. Right, and that is what we have for a bearing. So that KT value would be 2.5. The torque is what we calculated, and then we will have the bending moment at B. Right, so we have 3 regions within point B. So we have D1, we have D2, which is due to the key, and then we have D3. Now, of course, we could see that because the sharp fillet K is higher than the keyway K, we could automatically drop out the D2 and D3 and just use 2.5, because obviously that will give us a larger diameter because the same equation. Right, but we will keep it in the table just for now when we develop the table. The next step is, or the next component is at region C. So again, we have a KT value, and this will be a well-rounded fillet. So that KT value would be 1.5. We have a torque, because the torque is flowing through there. Then we have the bending moment at C. Right, so again, these bending moments would be the resultant bending moment. Similarly, for the key, you have KT is equal to 2. You have a torque and you have a bending moment at C. At this end here now, we have a retaining ring, or we have a circlip. So KT is would be equal to 3. Our torque now is 0 because the torque goes up again through the gear, but we will have a bending moment at C. Right, so remember at all these points, we also have shear force. We have shear force at A, shear force at B, shear force at C, shear force at D. Right, and we could use the shear force equation also for that minimum diameter, but we will do that in the table, but you will see that if those values are a lot smaller than the other equation, so we will ignore it, but we will have it in the table. Next up, we have the bearing. So the bearing at D, again, this would be, because we have a step there, and for bearing is a sharp fillet, so KT would be equal to 2.5. Our torque is 0 because the torque does not flow through there. Our moment will be MD, and our shear force will be VD. Right, I think MD would be 0. Right, but you could always check to make sure. And VD, we will have a VD. Right, so we could use these regions. Right, we could set up the table so that we will have a table with one column. We will have A, and then calculate D1, D2, and D3. Then at B, we will calculate D1, D2, D3 for the 3 regions within B. At C, we will calculate again the 3 regions, D1, D2, D3. And then for point D on the shaft, again 3 regions. Well, 2 regions, 1 and 2 due to the circle. Right, so the circlip, I did not write it in here. The circlip KT will be 3, torque is 0, MD, and so, and I run out of space there. Torque is 0, we have MD, and then we have VD. Right, so we'll be setting up columns for A, D1, A, D2, A, D3, B, D1, B, D2, B, D3. So this is how we're going to do it in Excel. C, D1, C, D2, C, D3, and then D, D1, D, D2. Alright, so once we enter the equations once, well, of course, we just drag it on in Excel. Okay, so before moving on, I just now said that you would have a circlip on the end here to hold the bearing. This is not true. The bearing normally is held on by its tight tolerances. So you could actually move this last term here. You could also move DD2. So all we'll be considering is the sharp fillet here. Also, at point B, you could see here that the actual diagram from the textbook that I got the question from, they actually have a cutout here as if there's a key. So there is no key, right? So there is no key. So there's no KT value or anything like that here. So all we would have really is a D1 value and a D2 value. Right, so we have a D1 value because of the shoulder, and then we'll have a D2 value because of the shoulder, which is a sharp fillet. Right, so there's no key as drawn there.